First of all, thank you very much to invite me in this year's GTT meeting. My name is Jung from Seoul National University. Today, I'll show you the overview of what we have done for the process simulations in steelmaking using the FactSage thermodynamic database and the ChemApp software. This is the overview of our consortium project started in 2009. In our consortium project supported by the 13 international companies, mostly in the steel industry, we have developed both thermodynamic database and the physical property database for our members. And in addition, we start to develop the process simulation model using the so-called effective equilibrium reaction zone concept from 2012. In this simulation model, we can predict the changes in the chemistry and the temperature of the steel and the slag during the plant operation. So many of our consortium members want to use these simulation tools to their smart factory application. And this is the main topic I want to show you today. Smart factory is the huge issue in the steel industry recently. In a short word, the goal of the smart factory is the improvement of the plant operation based on the AI and the machine learning analysis of the big data obtained by the sensors in the plant. One of the key components in the smart factory is the digital twin, and which can exactly simulate the plant operation. So by using this kind of the digital twin, we can monitor what can be happen in the plant, and also we can do the simulation and optimization of the process. And also we can do any kind of prediction of the possible scenario outcomes. And many companies also want to use this digital twin as an education tool for their new employee. So in this slide, I want to present critical weakness of the big data-based optimization. So let's assume we have a lot of data obtained in the current operation range. Then, based on this data, we can make a very nice AI model or machine learning model, which can reproduce our plant operation. But now, if you want to produce the new kind of steel, and also if you want to change your process condition dramatically, then there's almost no data available in the plant. And even though there's very few data is available, AI or machine learning cannot tell that whether this data is noise or real data. So if you believe this data is the real data, you can change the operation in this way. Or if you don't believe this data, then you can make original curve like this. And as an AI or machine learning cannot make this decision, and also any kind of most of the engineer cannot dare to make this kind of decision. So this is one of the critical weakness of the current big database optimization. So in the other word, the big data analysis is very good for the interpolation, but however, it is very bad for the extrapolation. But if there's the change like this kind of the curvature change, this should be based on some physics or chemistry. So we believe that fundamental thermodynamic and the kinetic knowledge can tell that whether the operation can have the actual curvature here, or it can go straight down like this. So that's why we want to make a digital twin model based on the thermodynamics. This is the two examples we can see for the nonlinear behavior of the property with the operation condition. So for example, on the left side, we can see the oxygen content change with the aluminum. So this is aluminum deoxidation curve. And we can see oxygen content is decreasing with the increasing of the aluminum content up to about 1%. And after that, we can see the increase of the oxygen content with the increasing of the aluminum content. So in the plant, typically we have the data up to about this range. So if the AI model is trained based on this data, AI model cannot make a prediction on this side of the region. And this is the dephosphorization of the BOF by using the slag. So when you increase the FeO content in the slag, the dephosphorylation capacity is keep increasing up to about 20%, and then it's declining like this. So if the current operation in the plant have the data only up to here, then AI cannot make a decision what will happen after this actually the region. So if you go to the high FEO, AI can make decisions, say that it doesn't change the dephosphorylation capacity, or it can even tell it can keep going up with the increasing of the FEO. But in reality, it's declining like this. So this kind of thermodynamic value is very important to give the more reliable digital twin development. There are two approaches to simulate metallurgical processes. Many research have been done based on the CFD simulation. In the CFD simulation, we can see how process parameters change the fluid flow in the vessel. Unfortunately, in this approach, we can use only simple thermodynamic calculation. Our approach is to use the thermodynamic calculations as a base of the simulation and use the kinetic mass transfer from the CFD simulation or plant operation data. In this approach, we can more accurately monitor the changes in the chemistry and the temperature of the steel and the slag. This slide shows you the concept of the effective equilibrium reaction zone model we proposed in the 2012. Let's assume we have the chemical reaction between the metal and the slag, and we can assume the chemical reaction at the interface is very fast, and it can approach to the equilibrium state at the high temperature processes. Then the change in the chemistry in the steel and slag is mainly controlled by the mass transfer at the steel and the slag side. So in the classical approach, this reaction kinetics was expressed by the mass transfer equations. In the real plant, however, we have to deal with many steel components and slag components simultaneously. So it is very difficult to solve the mass transfer equation for each element. In the effective equilibrium reaction zone model, we assume overall mass transfer coefficient concept. That is, we assume a certain fraction of the volume at the interface from metal side and slag side can react at the given time at the interface. And the amount of the volume can be calculated by using the mass transfer equation, as you can see here. So once that chemical reaction happens, then the reaction product can be homogenized by the metal and the slag side. And this kind of the iterative process can be done with the time. And of course, with the time, the mass transfer coefficient can be changed by the operation condition that can be reflected inside of this volume calculation, and then it can continue for the chemical reaction calculation like this. And in the old thermodynamic calculation, we are using the FactSage thermodynamic database. In this way, we can track the mass balance of each element very accurately. And also one of the another advantage of this kind of the approach is the heat balance calculation. So whenever you have the chemical reaction at the interface between the slag and the metal, for example, then a certain amount of heat can be generated or a certain amount of heat can be sink, depending on whether it is endothermic reaction or exothermic reaction. So because we are using the accurate thermodynamic database, so we can tracking all the heat amount during this operation, and they can give us very accurate prediction of the temperature with the time. This is the example for the ladle furnace model. Many reactions can happen simultaneously in the real plant. So many interfacial reactions should be simultaneously considered in the process simulation. In the LF, for example, we want to remove the sulfur and oxygen impurity in the steel. So we are adding typically aluminum to remove the oxygen in the steel. And in order to remove the sulfur, we are adding the calcium oxide to the slag and promote slag metal reaction by using the the gas injection from the porous plug from the bottom. So depending on how much gas we are injecting, the mass transfer inside of steel can be changed, and they can change the desulfurization reaction. So in order to also control the final steel chemistry, we are adding the ferroalloys. And also, in order to control the temperature of the final steel, we are doing arcing through the arc on the top here, and part of the arcing heat can transfer to the metal, and part of them can transfer to the slag. So of course, we can also consider refractory dilution in the slag side, and also heat loss through the air and the refractory side. And also one of the important impurity is inclusion. So we have to also consider modification of the inclusion and the removal of the inclusion simultaneously. And if there's the difference between the temperature between the slag and the metal, then naturally there's the heat transfer can happen. So we have to even include the heat transfer equation between the steel and the slag to find out the final temperature accurately. So all these kinds of things can happen simultaneously, and so we have to consider all these kinds of reaction every time step in the simulation. And on the right side here, you can see the relationship between the mixing energy and with the mass transfer coefficient in the steel. As I mentioned before, if you are injecting the gas through the porous plug here, it can promote more mixing in the steel side, and it can change the mixing energy, and that mixing energy can influence the mass transfer coefficient. And this data set is obtained from the Tata Steel by using the plant sampling. And by using those kinds of sampling data, we can make our own mass transfer coefficient depending on the mixing energy equation here. Now, after fixing a couple of the key parameters in the process model, we can start to do the prediction of the operation. So this shows you the profile of the aluminum, silicon, and sulfur content in the steel. And you can see the line, solid line is our prediction, and the dotted, all the symbols is from the plant sampling data. As you can see, Tata Steel did a huge amount of the plant sampling in order to make sure that our prediction is accurate or not. And you can see slag chemistry change with the time, and you can see temperature profile change with the time, and also even inclusion composition change with the time. As you can see, all these kinds of the very sensitive data can be well predicted by the present simulation model. Of course, the parameter we are using for the Tata Steel can be different from the other steel plant. And this is really depending on their operation condition and the dimension and the operation style. So based on those kinds of the real plant data, we can tune this kind of the operation, we can tune the parameter for the process model. Over the 10 years, we have done many process simulation models. And so, for example, I just show you the ladle furnace model for the Tata Steel, and also we use the same model for SEA and the Hyundai Steel with a slightly different tuning parameter. And we did also BOF converter model with the Hyundai Steel, POSCO, and the Best Alpine. And we also finished the electric arc furnace model with the Hyundai Steel and the Nucor Steel. And also we made the RHD gas model, which was tested by the POSCO, SEA, Hyundai Steel, and the Tata Steel. And we also have our own tundish and the mold flux model, which can be used for the mold flux design. And recently, we also work on the tank degas model and the AOD for stainless steel. And now we are moving to the next generation electric arc furnace for the decarbonization in steelmaking. In the past, when we developed the process simulation model, we used the so-called package macro processing code, which is already embedded inside of the package. And however, we found out that package macro processing code based model is very slow. So recently we switched our process model to the ChemApp, which gives a much fast calculation result. But even macro processing code is the simulation using the macro processing code is slow, but it is very easy to make a process model in the beginning and very easy to change it. So even in this day, when we develop the new process model, we first start with the package macro processing code and then test all our concept. And then once we believe that our model is ready, then we change this one to the ChemApp-based model. So by changing to the ChemApp-based model, we can increase the speed of the calculation, which can be even faster than the real operation in the plant. As I showed you just before, we have made many process simulation models, which can be directly used in the steelmaking plant. And many of these models was very well adopted by our consortium members. And for example, this is the overview of the smart factory plan in the Tata Steel in Netherlands. And one of the key components of the Tata Steel smart factory plan is the process simulation and the digital twin. And inside of this process and the digital twin, they are using our process simulation model as one of the key tools to train their level 2 model. This is another example from the Hyundai Steel. So as you can see, Hyundai Steel using the integrated simulator and the guidance model to improve their product quality. And here the integrated simulator is basically our process simulation model, and which help to improve their guidance model. So we are actually pushing our current process model to the next actual level. And so as we use the ChemApp, the calculation speed is faster than the real operation. So we want to make this process simulation model as a scheduling model for the plant. So that is, once you decide what kind of steel product you want to make, we can do the simulation before the operation, and we can give the guidance for the operation parameter. And of course, during this kind of the operation, we can check their real sampling data, and if necessary, we can do the minor actual correction in the process calculation, and then we can provide additional guidance data continuously. So in this way, we believe that we can replace the level 2 model in the plant by using our process simulation model. And recently, we started a project with Hyundai Steel and POSCO and SEA Steel in Korea to prove this concept. So far, I show you our process simulation model. And as I mentioned before, this process simulation model is based on the thermodynamics and the kinetics. So we believe that this process simulation model can do the extrapolated prediction out of the current actual process condition or current steel grade. So that means this kind of the process simulation model can be used as a next generation digital twin, which can improve the steel quality. So with that, I want to thanks for your attention. Thank you very much.